Hello everyone, today I wanted to talk about longest prefix matching, which is the last topic which we'll discuss at layer 3. We'll revisit layer 3 if at all we get time at the end and look at a few topics like SPGP and things like that. Right, so the last topic is longest prefix matching, and what is this? So just recall what supernetting is. So in supernetting we said that you have a large number of smaller prefixes, or in fact these are longer prefixes. So this is the prefix length, and these could be aggregated by some ISP down the line, and it could advertise a shorter prefix. Okay, like this, and maybe several other prefixes maybe get aggregated with this one too, and so maybe somewhere down the line this particular autonomous system might aggregate this even further. So it might announce something like 142.31/16. Okay, just based on the addresses over here. Okay. So this might happen, and this helps a lot in reducing the size of the routing tables. So somebody, for example, who has just this prefix has one entry, and maybe it hasn't received all these prefixes, so it doesn't have routing table entries for all of them. Okay, so that reduces the size of the routing tables of various routers. So that's a good thing, and this is what we studied last in one of the earlier classes, and we called it supernetting. Now it might happen that somebody actually gets a path, let's say this particular AS announces its prefix this way, and there is somebody down the line here, let's say, who might get this advertisement, and it also might get this original prefix. So what's going to happen over here? So for each unique prefix reached, it's going to use the BGP rules, and it's going to choose a particular path. Okay, and so let's say that this has come from this particular autonomous system. Let's say AS1, and this is whatever. Let's say that we have a direct connection, AS2, AS3, and so on, right? Let's say this is AS4. So suppose this particular AS, let's say it's decided to use this particular path for this, I beg your pardon, this should be what, 24. And it's decided to use this path for this particular prefix. Okay. And for this prefix, let's say this one, it has decided to send the packets this way. Okay. So you might wonder, what is the AS path for this particular prefix, right? Because I mean this particular prefix is being created over here. So as you can imagine that the prefix is going to end over here. Okay, so I mean the AS path would be just this AS number. Okay, because you never know. I mean, he can't advertise this particular path to this particular AS for this larger prefix. That's not possible. Okay, so anyway, basically this autonomous system, so let's call it AS5, has decided that for this particular prefix it is going to use this path, and for this particular prefix it's going to use this one. So suppose it gets AS5 gets a packet with the destination IP matching this particular prefix. Whatever, slash, whatever, 20, let's say. Suppose this is the destination IP. Now there is an issue, so maybe the packet comes in over here to this particular router, and the router has entries corresponding to both prefixes. So this particular router, let's say it has a table which looks like this for a prefix, and let's say there's a next hop, and it has 142.31/16, and it has some particular next hop, and it has a longer prefix. Now there is an issue here because this particular IP address matches both the prefixes, right? The first 16 bits are indeed this, and the first 24 bits do match the first 24 bits here. Okay. So now we are in a bit of a fix. What do we use? I mean, should we send it along this path or this path? Okay, so should the packet go this way or this way? So what we want to do is we want to be consistent everywhere, so everybody needs to follow the same rule. Okay, it shouldn't be that this person says that I will go by the shortest prefix, which in this case would be this, and somebody else says that I will go with the longest prefix. Okay, it shouldn't be that somebody randomly chooses any one of these. So there has to be something consistent done by everybody else if we want to ensure that routing loops are not going to take place. So what are we going to do over here? And the rule is that you choose the longest prefix. And the longest prefix in this case is going to be this one. So intuitively, why do we do longest prefix? Why don't we do something like shortest prefix? Okay, so if you think about it, in the autonomous system which actually has this prefix, it is going to advertise this one, which is the longest prefix. And as you move further away from this autonomous system, on some particular path in this graph, right, you will find supernetting taking place and shorter prefix getting advertised. Okay. So if we use something like shortest prefix matching, it may happen that we will actually send a packet further away from the destination autonomous system. There could be a situation where that occurs. Okay, but if you use longest prefix matching, it guarantees that the packet will go towards the destination AS and finally reach it. Okay, so this is the reason why we do it, and so everybody in the internet does a longest prefix match. So this autonomous system does a longest prefix match and it goes here. Okay, so suppose somebody else, let's say this autonomous system got a packet here with a destination IP matching this particular prefix. What would it do, right? Or maybe to make it more interesting, let's say that this one got a packet with destination IP 142.31.135.7. Suppose it got something like this. Then what do you do, right? So clearly if you did something like shortest prefix matching, I mean, maybe you might get an advertisement even from this AS. It might come back here, or it might come back through some other autonomous system. You may have an advertisement here coming for this larger aggregated prefix. Okay, so this one might get the /16 142.31 might get an advertisement like this, right? And in this sort of situation, you can see it makes sense to send it in the longest towards the longest prefix. If you send it towards the shortest prefix, you would send it the other way. It would come over here, okay, which doesn't make sense. So everybody follows the longest prefix matching. So this autonomous system will send it this way. This one will send it here. If this particular autonomous system gets a packet, it will look in its own routing tables, and of course it will see this one has been advertised. There will be only, in this particular example, there's only going to be one entry, so it will send it this way, right? And the packet will go this way. So longest prefix matching ensures that the packet reaches its destination. Okay. So essentially at a router, core router in the internet, you might have millions of packets coming in every second. And for each and every one of those packets, the entire routing table has to be very quickly searched. And you want to very quickly find out the longest prefix match for the destination IP. Okay, so there are hardware solutions for that. You can look up, if you're interested, content addressable memory, or CAMS. Which would give you a very quick lookup, right? It will essentially search in one shot. It will search the entire table and tell you all the prefixes where there is a match, and then you can quickly find the longest one among those. Okay, so all of this has to be optimized a lot, and we've simplified things a lot in the internet. So core routers don't have to bother about higher layers like TCP or the application layer and so on. They're mainly looking at layer 3 and below. And layer 3, this lookup has to be done very quickly, right? And of course, because like in the live session we discussed that there are issues about actually forwarding packets when you have very high speed routers from one link to the other. Okay, so all of this becomes more and more challenging as you go to higher and higher speed networks. So this is the last topic I wanted to cover in layer 3. And now I want to talk about layer 4, which is the transport layer. So we've discussed about the file layer, the data link layer, the network layer. And what does the transport layer give us? So at the application layer, we have a lot of freedom. We can install any application that we want. So we can have various applications. And that's one of the nice things about the original internet. They had just a few applications, not too many. But they designed it so that you could add essentially any number of applications that you want. Okay. Right, so it's very flexible, and the application layer is extremely rich. I mean, you can come up with new things. Nobody had thought of anything like social networking or peer-to-peer networks and so on at the original time the internet was developed, right? But you can come up with newer and newer ideas. Right? Nobody would have thought of something like Amazon, right, or e-commerce and so on. But because the internet is so flexible at the top here, all these applications are possible. Right? So from these layers below that, at the transport layer, things get ossified, and all these tasks essentially are pushed into the operating system and into the network drivers and so on, right? Just to make it easier, when you're building an application, you don't have to worry about all these tasks, about IP address lookups or where to forward the packet and things like that, right? Or framing errors or modulation and things like that. All of this is taken care of by the lower layers, and we are free to put our brains into developing an application we want. So what does this transport layer give us? One of the things is demultiplexing. So network, let's say we get an IP packet which is meant for us, right? It comes to the right IP address. And these packets could be meant for very different application. Maybe it's meant for application 1, 2, 3 and so on. So the transport layer is going to do this job of demultiplexing. Multiplexing means putting together from different sources, let's say, together, and demultiplexes is doing the opposite, right? Splitting it up into sending it to the appropriate application. So this is the most basic task of the transport layer. And how do we do this? While using something called port numbers. In the lab class, in one of the lab sessions, you will have written some socket programs, and each of these, let's say we give some particular port number. Okay. So it's a web server, for example, it might be 80. Right, and there are standard port numbers for the well-known applications. Okay, those are reserved. They are not other applications are not supposed to use those. Okay. So this port number is there in the transport header, and we will be able to use that in order to send to the appropriate application. Okay. So if at all you want a transport protocol which does only this, then you should use UDP, which is the user datagram protocol. So UDP pretty much gives us just this. Okay, so there is no nothing special that it does. But what else do we want from the transport protocol? So suppose we don't want this, we want other features. What might we want the transport protocol to do? So let's think, suppose I was doing a file transfer. So this was my application. I wanted to just download a file from somewhere. What is going to happen? So this is the large file. Let's just write it this way. So let's say this is hundreds of megabytes, right? It's a massive file. So what are we going to do when we transfer it somewhere? We can't send it in one packet. We know that Ethernet is only going to accept something like 1500 bytes. So IP also will pretty much try to keep the packets small enough so that it isn't fragmented. Okay, it's possible for the IP layer to do fragmentation where a larger packet is divided into smaller parts and it's recombined somewhere else. Okay, that's a very complex task to do. But we'd rather not do that because that's making the IP layer do all sorts of complicated things. Right, so we normally keep our IP packets to be smaller than 1500 bytes because we would expect Ethernet to be there somewhere along the path. And we know if we send longer than that, then we'll have to divide the IP packet. Okay, so let's say we divide this into packets of 1500 bytes or so. So there are several of these going to be sent across the network. And we will call each of these at the transport layer, we will call it a segment. That is the term to use. Okay, so within the IP packet, let's say we have one particular UDP or TCP segment. Okay. So these segments are going to go across the network and they're going to reach the other end. So let's say that this is the source and this is the destination. And the routers in between, they figured out which is the next hop using a combination of BGP and the interior gateway protocol and so on. They use longest prefix matching, right? And everything, so, thankfully works. They are so complicated, but luckily everything works out fine and our packets get to the other end. But what can happen? What can go wrong? So sometimes segments may get lost. So packets can get lost. So some packets might get through and there may be some gaps when it reaches over here. This is the destination. Okay. So these are segments 1, 2, 3, 4 and so on. Maybe 1, 2 reach here, but 3 is lost and then 4, 5 gets through. Right? Then what might happen is that the path might change. It's possible that the routing paths actually change due to some reason. Right? Because it could be that a link failed or somebody changed the routing weights or something like that. The interior gateway protocol changed the routes. So what might happen is that, let's say this is 5, 6, 7, 8 and so on. What may happen is that 6, let's say 6 and comes. But then what happens is that, let's say that 7 and 8 went this way, or let's say this was the original path. And then let's say this became the path. This is the new path. Okay, so all of them are going this way, but then suddenly 7, 8 onwards came here, and let's say this was sooner, this was shorter in terms of latency. So 7, 8 might come before 6. Okay, so frame 3 was lost. And what you have here is reordering. So you can have reordering even when you have first in, first out at all these routers. So remember that what is first in, first out? For a queue, the first packet in is the first packet out. Okay, and normally in this sort of a situation, if there's FIFO, you wouldn't expect reordering. If you had a more complicated queuing scheme, maybe you will have reordering. Right? But usually you would have routers implementing FIFO, but still you can have reordering because of paths changing and so on, and they have different latencies. So suppose the transport layer didn't do anything and it just dumped this information back to the application. And somebody opened his PDF file, suppose it's a PDF file, it would look like complete garbage because there's one part of the file missing and some parts of the file which are completely reordered, right? Or even if it's a plain text file, forget about PDF, it would look very weird, right? And it doesn't make sense because the files could be very, very important. Every single bit can matter, right? Suppose this is a file which corresponds to bank data, for example. Right? Many of you are interested in financial jobs, right? They are considered to be hot jobs, right? So banking applications are very key, and clearly even a single bit flip in a file could mean something terrible happens, right? Bill Gates can lose all his wealth if one bit is flipped in his bank account. Right, and you and I can become Bill Gates if one bit is flipped in our account, right? So you can't afford to have bits which are missing or reordering and things like that. Okay, so what a transport layer can do is it can simplify matters for us. If we are building an application, we wouldn't want to do this whole business of waiting for lost segments or retransmitting and so on, right? So what the transport protocol can do and in fact TCP does this. In addition to just the business of demultiplexing and sending the packets to the right application by putting a port number, TCP is going to reorder packets and also what it's going to do is it's going to do reliable data transfer by retransmitting lost packets. I should say lost segments. Okay, so what is TCP going to do? So this data is not going to get sent to the application until, so 4 and 5 are not going to be sent, or anything after 3 is not going to be sent to the application until the third segment is received at the destination. TCP will just, it will send 1 and 2, it will send to the application layer, but this part will not go until this has been received. Okay, so this source is going to retransmit frame 3 or segment, I should say segment 3. Okay. And of course it's not going to retransmit any of these frames. So I mean, of course there's a mechanism to detect if a segment is actually lost or not, but let's say that works out fine because none of these have been dropped. So now it's the job of the receiver to actually reorder things. It will have to put this properly in the right position, and after, it will also not send 7 and 8 immediately because 6 has not arrived, and when 6 comes it puts it in the right location and then pushes this data up to the application. Okay. So these are two tasks. I mean, implementing them, this thing would be a little bit tricky, but not so difficult. And of course, this part has to be done with some care. And the reason is that the routers are not cooperating in this reliable data transfer. We said that they are just dumb routers which just work up to layer 3, and they forward packets as fast as they can. Because they are extremely fast, they can take millions of packets and send them out in the appropriate output link. But that's all they do. They are not, if a packet is lost at some queue, they are not going to retransmit it. Okay, it's the job of the end host, TCP running here, to retransmit it. So since TCP doesn't communicate directly with these routers, it has to infer packet loss, which is somewhat tricky to do, and we will see how that is done here. Okay. So these are two things, and TCP does a lot more, in fact. So it's quite heavyweight, I should say, compared to UDP. Okay. And if you want something in between TCP and UDP, maybe you want a subset of things that TCP does, then you're better off using UDP and having your own transport mechanism implemented at the application. Okay, so but let's see what else might TCP do. So let's look at one of these routers. And as we've discussed in various either lectures or in the live sessions, if this is an output link and these are various input links, so this is why I'm just showing it conceptually. Okay, so this could actually be one of these physical wires. Okay, I mean, it could be the same physical wire which is full duplex, getting traffic in both directions, but I'm just conceptually showing the outputs here and the inputs on this side. Okay, so each of them would have, let's say, an output buffer, and it may happen that lots of packets come in, and they are all meant for the same output link. So the input speed, incoming rate to this queue can be higher than the output, the emptying rate, because of which this queue gets filled up. So the packets get buffered over here. If we know that if the queue is full, then it's called a drop tail mechanism. If you can implement a drop tail queuing mechanism in NS3, right, which you used in the lab. So drop tail essentially means that when the buffer gets full, you drop the packet. You just throw it away. You don't care the least bit about it. And if this happens, then we say that congestion has occurred. So the queue is full and packets are dropped. It's like a traffic jam on a road. Too many cars have come in and they're all sort of stuck in a particular place. So if we just used UDP, for example, okay, so let's say that it's just plain UDP, which is just essentially when it gets information from an application layer, it's just going to add an appropriate port number and send it off, right? That's all it does. And if every application uses UDP, then it may happen that this congestion prolongs for a very, very long time, right? The input rate stays the same irrespective of whether there's congestion or not, and that's a problem for the network because packets will keep getting dropped. There will be a very high packet loss rate. So what should we do instead? So TCP is clever in that sense. So TCP is going to infer that congestion has taken place, and it does something called congestion control. So what it's going to do is it's going to reduce its segment sending rate okay, so this is what I mean by sending rate is the data transfer rate. I want to slow down because there's like a traffic jam occurring somewhere along the path. So if everybody is using TCP, you would expect a lot of them and hopefully all of these TCP flows which are sending packets over here, okay, they would all recognize that congestion is taking place and they would all back off. So the input rate overall would decrease, hopefully to less than this output rate, and then the queue would get completely emptied and become fully empty, and congestion would go down, right? Because the queues are empty. So this is what TCP is supposed to do. Okay, actually in practice things may be a bit complicated because each TCP connection or flow is working independently of the others. So it may happen that some TCP flows back off because they detect congestion and some don't. There may be a weird situation like that which happens. But in general, enough of them will back off so that this queue actually empties out. Okay. So TCP does congestion control, which is non-trivial to do, as we'll see. Okay, and lots of TCP protocols have been proposed to do congestion control. Okay. So I'll add to that. So besides these two, it does congestion control. And there is also something called flow control. So what is flow control? So let's say this is the source and these are the various routers along the path to the destination. So congestion control takes care of if congestion occurs in one of these routers, okay, so this source is going to infer through some mechanism, either from packet drops or it looks at round trip times and things like that, and it infers that congestion is taking place and then it backs off. But congestion can also take place here, so at the destination. And this is what, if you handle the congestion here, it is called flow control. So why is there a different mechanism for the destination? And the answer is that the source and the destination are communicating directly at the transport layer. So TCP is sending out packets and getting acknowledgements and so on. And in fact even data can go in both directions. TCP allows that. A single TCP connection, you can have data going in both directions. Okay, but typically you would, I mean most of it would be in one direction. Let's say you're downloading something from a website. Usually you are getting data from there, but it doesn't have to be there. For example, if you're doing let's say a search, okay, you're sending to a Google search engine, right? You type in something, data goes one way, and then the web page shows up. So the web page is going in the other direction, right? So there's constant communication. You're sending data potentially in both directions, but also acknowledgements could go in both directions, where you acknowledge receiving data which is coming from the other end. So when you have explicit communication between the two, you can do this congestion control at the receiver much more. If it happens at the receiver, you can do it much more precisely. You don't have to infer that communication is that congestion is taking place here. The destination can just directly tell you that congestion is happening, so please slow down. And you might think, why would that happen? Well, because this machine also takes some time to process information that it gets, right? Maybe there are hundreds of applications here, and maybe that particular machine was not able to handle the packets coming in for a particular application. So those packets could be stuck at the transport layer and they haven't yet been read at the application layer. And in that particular case, there could be congestion because TCP has some buffer, and the buffer could be getting full over here at the destination. So there's a separate mechanism to do flow control. It's much more straightforward, in fact, because there's direct communication at the transport layer. So TCP does all of this, and as you can imagine, it's quite a complicated protocol. So a lot of work happened in TCP, especially in the 80s and 90s. Somebody called Van Jacobson, so he in the 1980s came up with the first flavors of TCP, and those days they were experimenting, and sort of they came up with some rules of thumbs to do things, because it's non-trivial to especially to deal with this congestion control. And in the 90s and maybe early 2000s, lots of work was done for TCP, improving TCP, because what happened is the internet went from very low speed links, like we started out with something like 56 kbps, right? And already by 2000 they were dealing with 10 gigabit links, or gigabits of speeds, right? And now it's even higher. So when you go to higher speeds, typically you need better protocols, but you have to keep TCP also sort of backward compatible with other TCP protocols which are already out there and so on. Right, so Van Jacobson and Sally Floyd and others were the big names in the TCP in the 90s till the early 2000s, right? And of course now, and some of you in the class too have already read some papers on TCP for data centers, right? So within the data center, you have essentially a huge large network of all these servers all over the place, and you have to very quickly get data from one server to the other, right? You and I might do a simple Google search, but Google has to very quickly search through all the data spread out across multiple servers in its data center. And as we can see that TCP can have lots of delays, so you want to optimize TCP for your own data center, right? So the data center TCP and so on, which people have been talking about for the, let's say, the, in the last decade or so. So this is what the headers look like. So we are using the same convention which we use for the IP header. So bit 0 to bit 31 is shown in the first row. And then of course we start with 32 onwards, right? And each row corresponds to 32 bits. So here we have the source port, that's 16 bits. And the destination port is here. Okay, the length of the whole datagram, and checksum, and this is followed by the data. The UDP header is not too large, just 8 bytes. Okay. So TCP does a lot more than just putting in a port number. So the header looks like this. So again we have the source and destination ports. And after this, we have a sequence number. So this is essentially going to say that the data that comes in this particular segment, where does it really lie in the whole stream of data that was sent, right? So we'll see how exactly it would be used, but essentially it's telling you that this chunk of data that's coming in, where is it in this larger file, let's say, which I am sending. Okay, so the sequence number would tell you where in this, let's say that you get a particular segment starting here, it will tell you effectively the byte number over here, right, starting from the beginning. Okay, so we'll see, of course, that the initial sequence number is randomly chosen and what that means and why that is done. But of course this sequence number for a particular segment is going to tell you it's going to tell you effectively how far you are from the beginning. So sequence number, and since it's a two-way communication, you can have you can send your own data and you will say what the sequence number for the data is, but you can also acknowledge data which you got in the other direction. So you have an acknowledgement number. Okay. And after that we have various fields. We have some flags. And an advertised window. And then there are things, checksum and so on. Right, so we are not looking at all the fields here. Okay. And then of course this is followed by the data. So how many bytes is this? Well, it's 1, 2, 3, 4, 5, 20. Okay. So even if you're sending one bit of data at the application layer, there's a lot of overhead here. So if you're sending it via TCP, you have 20 bytes just of TCP and another 20 bytes for IP and so on, right? So you might end up sending a very large frame at the MAC, at the link layer, or even at the physical layer, even if it contains just a single byte of information at the application. Okay. So this is, it says this is going to say what byte number we are expecting next. Okay, you're telling the other person who is sending you data that I am expecting such and such a byte from you. I've got everything up to this point. So I've got everything from the initial byte you sent till the previous byte. And now this is the number of the byte that I'm expecting next. So sequence number is going to tell you byte number of first byte in this segment. And these flags, of course, these are single bits, so each of the bits has some information. There's the SYN flag, the FIN flag, reset, push, right, and several other flags. Urgent, there's an urgent flag and an ACK flag and so on. Okay, so what are these flags meant for? So we'll see that initially when you start a connection, you send out something called a SYN packet. And when you end a connection, you send a FIN packet. So when you want to close a TCP connection, you would send a SYN packet. And you identify that you're sending a FIN packet when you actually have that particular bit set. Okay, so these bits are set to 0 or 1. So a 1 in this position, in that this particular byte, is going to correspond. Essentially it means that this is a FIN packet. Okay, or if this is set to 1, it means this is a SYN packet and so on. Reset means you want to reset the connection. Okay, so that may happen in some case, and you might easily see that it's possible to do an attack using this. So suppose you know that there's a TCP connection going on, you could just fake sort of, you can send, maybe a third party can send, who's an attacker, he could send a particular TCP segment which has this particular bit set, and then it will reset the connection. So essentially the whole thing is, essentially the connection is ended. Okay. But of course this was put in for a purpose, I mean in case either party wants to really reset the connection. Okay. These we won't bother much about. When this particular bit is set, it means that the ACK number is valid, that an acknowledgement is included in the segment that I'm sending. So a particular segment doesn't always have to be acknowledging anything, right? So maybe you are only sending data from this side to that side. So the other side has not bothered to send you any data, right? So there are only this makes sense, the sequence number. So this ACK field is essentially left empty. You're not setting it to anything. So you wouldn't set this flag, it would just be 0. But in case you want to send data and send an acknowledgement for data which was coming in the other direction, you could do that, in which case you would set this bit to 1 among these flags, right? And then the other side would actually have to look at this because it has some useful information. Okay, so suppose we get an IP packet. How do we know if the next layer is UDP or TCP? You know, what is happening at the transport layer? And that is set in what's called the protocol field at the IP layer. Okay, so if this is set equal to 6, then that means that the next layer is TCP, or if it is set to 17, that corresponds to UDP. Right, so IP will know by looking into its own header whom to give the packet to next. Okay, whom to give the payload of the IP payload to next. Okay, and of course TCP or UDP will look at the port number in order to decide which particular application to give the payload. So this is the basics, and we'll from the next class onwards we'll look at the details of how exactly TCP works.